Stars, lightning, fire. These are among the first things that come to mind when people think about plasma. But what is this exotic state of matter? The three common states of matter, solids, liquids, and gases, differ primarily in the motion of individual molecules within a substance. But you can't just create plasma by making gas particles move faster. Instead, plasma is formed when the outer electrons of gaseous atoms are stripped away from the influence of their nuclei. This forms a sea of electrons, similar to that found in metallic substances. In this configuration, the medium is free to transport an electric current in the presence of an electric field, meaning that even insulators like air can conduct electricity in a plasma state, allowing for phenomena like lightning to occur. But creating plasma requires energy. Indeed, our entire universe was a giant pool of plasma for the first 370,000 years after the Big Bang, because the mass and energy of everything within it were so concentrated. This famous mapping of the cosmic microwave background radiation depicts the state of the universe at the moment this plasma collapsed and true atoms first began to form. But a controlled plasma can also be created artificially, without having to heat it up to incredibly high temperatures. Here's how. We begin with a tube containing a gas. Usually, a noble gas like helium or argon is used, so it doesn't react with its surroundings, but any gas can work, even air. Next, on each side of the tube, we insert a metal plate. These plates are connected to a power source that induces a voltage or potential difference between them. The voltage creates an electric field that would make any loose electrons within the tube fly toward the positively charged plate, which we call the anode. These electrons appear in the tube through a number of intricate processes, ranging from the photoelectric effect, by which a beam of light can knock electrons off of the negatively charged cathode, to tiny particles like neutrinos, pelleting the Earth from outer space and occasionally ionizing a gas particle, that is, bumping into an atom within the tube with the right energy and orientation to knock loose one of its electrons. And as these electrons are carried toward the anode, some of them ionize other gas particles. As you might expect, a chain reaction ensues. In addition, the newly ionized gas particles all begin to move toward the cathode and can knock loose even more electrons upon impact. This is known as secondary emission. The sum of these processes is given a very special, incredibly technical name: an avalanche. But you might wonder, just how much voltage do we have to apply to maintain an avalanche? The answer depends on two quantities: the pressure of gas within the tube and the distance between our two plates. This relationship, called Paschen's curve, is modeled by plotting voltage against the product of these quantities. But how come the minimum voltage required first decreases as pressure or distance increases, and then changes its mind? To understand why this happens, let's examine one scenario at a time. If the pressure in the tube is really low, let's say there's nearly a vacuum, then any electrons that are traveling from cathode to anode are less likely to bump into any gas particles and initiate an avalanche. Similarly, if the distance between the two plates is really small, electrons can make their way across without encountering many gas particles. In either of these situations, a really high voltage has to be applied to initiate the constant flow of electrons required for plasma. But high pressures and distances aren't good news either. In a high-pressure system, electrons accelerate for only a short period of time before hitting a gas particle, and usually haven't gained enough energy yet to ionize it. Meanwhile, if the plates are too far apart, the electric field between them gets weaker, and the resulting acceleration of the electron is low. In both of these cases, the solution is to increase the electron's acceleration by once again cranking up the voltage. So to form plasma using the least possible power, we have to set our pressure gap product to the minimum on Paschen's curve, not too small and not too large. The most common way to do this, without positioning the electrodes just micrometers apart, is to use a vacuum pump and reduce the pressure within the tube by the order of 1,000 times. In the case of lightning, which occurs at atmospheric pressure across incredibly large distances, one can only imagine how much potential difference there must be between the ground and the sky. But plasmas aren't just useful for keeping people entertained and physicists employed. In fact, plasma has influenced our science and technology in more ways than you can imagine. Neon signs and fluorescent bulbs both use plasma to generate light. In the case of fluorescent lights, you can see how the phosphorus coating on the left allows plasma to produce white light by absorbing its UV light and re-emitting it at various visible wavelengths. On an environmental note, companies like S4 Energy Solutions are using plasma to convert trash into useful products like hydrogen gas and carbon monoxide. To quote an article from Wired.com, "This isn't incineration. This is emission-free molecular deconstruction." Additionally, in the Science Education Center of Princeton's Plasma Physics Laboratory, plasma is being used to model astrophysical phenomena, including the Earth's magnetosphere and the Northern Lights. And through the laboratory's National Spherical Torus Experiment, or NSTX, scientists are using plasma to facilitate nuclear fusion, which they hope will ultimately provide an inexhaustible, safe, and environmentally attractive source of energy for everyone on Earth. Plasma has been at work shaping our universe from the very moment it was born, and now, here on Earth, we are beginning to capture and utilize its magnificent power.